Well, good afternoon, everyone. I'm very, very pleased to see such a large audience. I think this is the largest audience I've seen in this room since pre-COVID times. I'm very pleased to introduce Professor Irfan Siddiqi, who will give our colloquium today. He received his bachelor's degree in chemistry and physics at Harvard in 1997. And his PhD in applied physics at Yale in 2002. He continued at Yale as a postdoctoral scholar from 2002 to 2006. Irfan then joined our department as an assistant professor in 2006. He is now a professor of physics and EECS as the director of the Quantum Electronics Laboratory. He's also a faculty scientist at the Computational Research and Materials Sciences Division of Lawrence Berkeley National Lab, where he is director of the Advanced Quantum Testbed. Irfan has, over the years, taken many administrative responsibilities in our department. For example, he was department summer chair during 2014 to 2018, and vice chair from spring 2017 to summer 2018. Irfan has won awards and distinctions for his work, of which I will name just a few. He won the American Physical Society George E. Valley Jr. Prize in 2006. And then in 2021, he won the APS John F. Keithley Award for Advances in Measurement Science. He is a fellow of the American Physical Society, and in 2016, he was a recipient of the UC Berkeley Distinguished Teaching Award, which tells us that his manner of teaching and speaking rival that of his level of his research. The title of his colloquium today is The Dawn of the Quantum Computing Era. Please join me in welcoming Professor Siddiqi.
Good afternoon, everyone. And indeed, it is a pleasure and an honor to be introduced by Professor John Clark. Thank you for that introduction. Let me also convey my thanks to Professor McKee and the colloquium committee. It's nice to be giving a talk on the home front. And thanks to everyone that has shown up in for an in-person talk, and it's really great to be returning to times as usual. So we certainly hope that remains that way. The subject of the talk today includes this buzzword, quantum computing, which indeed has entered many circles, including the popular press and also scientific circles. But I wanted to really do this topic some justice. So I gave it an additional word, which was the word era. Because quantum computing may be viewed as a singular point in history where we have achieved a certain type of machine or computation. But in reality, what we are experiencing is a new phase of how we interact with this theory of quantum mechanics. And that, I think, really deserves the word era. And what I would hope to show you during the slides is this two-sided coin. On one side is really testing quantum mechanics and quantum phenomena in a way that was only imagined for many decades. And the other side of the coin is technology that moves forward. With any discussion of science that we do in our lab, I must start with an acknowledgement. The science that we do really takes a village, right? And indeed, this is just a snapshot of the local village of graduate students and postdocs that are here. And our research is really described here. But the support and infrastructure underneath that goes well beyond that. And in fact, I see the leadership of LBL here, and I'm grateful for your support. And I see Ardeen, who we're meeting for the first time in person. Thank you in advance for the support that we have. So really, it's a village that can't be contained on a slide, but the websites hopefully are more appropriate for describing what we do and the folks that fuel that poll. If you promise to go to sleep. We are in a democracy. Vote if you want the second light off. All right. Thanks. Let's talk about this change of interaction with quantum mechanics. Yeah, I know where it is. One advantage of teaching in this room. Okay. One thing about the interaction with quantum mechanics. There's this beautiful book written by Manjit Kumar, in particular of the title, Einstein, Bohr, and the Great Debate About the Nature of Reality. And you see these two gentlemen from the image from the Emilio Segrè archive, thinking and debating about quantum mechanics. So what are the takeaways of this theory? What was amazing is that theories of physics prior to this really had this motivation that if you looked hard enough, you could see the inner workings of any system that you're looking at. If we couldn't understand something, it was because we didn't have a good enough pair of glasses, the telescope of Galileo, or what have you. And quantum mechanics started to tell you something slightly different, telling you that our observations of the world around us reflect only some aspects of a much more complex reality. And what's very interesting is there are principles that tell you that you cannot actually know all of those aspects at the same time. And this is really a change of philosophy of physics. Why would you ever want to believe that? Perhaps we can come up with a theory that's better suited to everything around us, and that doesn't have this substructure. It turns out this is not the case. Right? In fact, we need this underlying structure to explain basic observations of the part of the world we can see. And we've tried very hard in decades to find hidden variables or other things, but quantum mechanics seems to be the law of the land. So what's changing? We are really entering an era where this substructure, this entanglement, I will talk about this, is actually turning into an engineering resource. And that's very different than simply observing quantum effects. We're using them to do something. So what does quantum mechanics change about computing or information processing or sensing? I want to share with you today two quotes from Rolf Landauer from IBM. The first one is here, where Landauer said information is physical. And you can think about this. However you want to store information, you need some kind of physical system, whether it's beads on a string, DNA, or what have you. And now, of course, quantum systems. And so, of course, the Chinese knew about this as other folks for many millennia. You can store information on an abacus, you can process it. And you can also do very, very fancy things. This is the quantum processor, which is due to be deployed by the Aurora machine at Argonne. I see our associate lab director of computing recognizing probably this processor. You may even have held one in your hands. So what's different about this? The Ponte Vecchio actually is one of the oldest, if not the oldest, bridges in Firenze, in Italy, and survived all the wars, and it connects many different parts of the city. And this part also has different core and what have you that are connected by bridges. And what's amazing is that even though you've shrunk the size of your abacus beads to 1/1000th the diameter of your human hair, you still can't solve a whole class of problems by shrinking the size of your bit. And that is because the structure of how you store that information and how you process that information is fundamentally the same in both devices. And it's not in mechanics. I'm going to go through that in the next couple of slides. You see also titles like this, right? Mind-blowing technology goes mainstream. People also putting money into it to support that. So this is equity investment, 800 million and climbing. So quantum is turning into a big business. And it's a business for what? Well, what are those mathematical functions that could be tackled by a quantum machine that classical machines have developed? One of them is diagonalization of certain types of matrices, in particular sparse ones. And if you could do this task, this underpins so much of the science that we do in simulation, optimization, machine learning, cryptography, what have you. And you can see the numbers associated with these applications. This is really where the promise is in this moment. And I can see cynical physicists like myself thinking, that's not going to happen. How far away? This is just hype, right? We're far away from that. don't think it's the way. So I'll show you that. And in fact, I'm going to give you a slightly different twist on how a physicist perhaps thinks about quantum computing. You see, for computer scientists, there's a different way to look at it. You think about problems that are in a different complexity class, right? Classical machines just can't solve certain problems. Quantum machines can solve them perhaps much, much better. But like the practical problem may be simpler. What if your quantum computer doesn't solve exactly the problem you want, but it gives you some valuable information, some valuable insight to a problem? Let me give you an example. If you want to develop a pharmaceutical drug, each drug, roughly speaking, costs $2.5 billion to develop. That's a lot of money. Okay. Why? Preclinical research selects 0.1% of the small molecules for clinical trial. Okay. And then 10% of clinical trials are successful. And the real problem is quantum effects in molecules evade classical simulation. So you can ask yourself the question, well, can I really solve for the ground state of all of those molecules? That's a hard problem. Or maybe I can just change this 0.1% to 0.5%, right, by having some quantum insight. That would change an entire industry. Okay. And in fact, that motivated us in the early days to look at hybrid algorithms. And this is work that was done jointly at LBNL. Mike, this was the first experiment we did funded by your LDR at LBNL. Okay. And the idea was the same. Can I use quantum to somehow enhance my understanding of the physical world? So it may not be so far away. How many of you understand entanglement? It's better than me. So yes, it's a mathematical tensor product which changes exponentially the Hilbert space size. So aside from that, I was thinking of giving you a physical example of things that are entangled. So if you're getting old like me, you've probably been in one of these machines. Right? So it's an MRI scanner. Quantum mechanics is all around us. Takes the water molecules that are typically there, applies a magnetic field in a given direction, and the spins of those nuclei align or anti-align. And that's how you find them. If you look at those spins, they're either up or down. Yeah, but sometimes they also point the other way. Right? So you can prepare them in a state that points sideways. Okay? And see, the quantum mechanical question is the following. If your detector reads up or down, will you have sideways? Of course not. You can only read up or down. So the way to reconcile that is that if you make a measurement shown on this spherical representation, you would measure 50% of the time up and 50% of the time down. Okay? Typical measurement of a spin-a-half system. Automatically, what this is telling you is that all of the other points on the block sphere can exist. You just can't measure them because your detector measures up or down. Okay? So quantum systems can exist in many different configurations, even if we can't observe all of them. So if you can tap into that substructure, you can do something more complicated than simply a bit that's 0 or 1. Okay? But that's one bit. Let's go ahead and build a computer with many bits. In this case, I've put some in a square and a square. Okay? Let's build a quantum computer one spin at a time. But unlike MRI, which will measure an ensemble, you're going to measure the collective response of a piece of tissue. I need to measure each one of those. That's this subject part. There are seats here if you like, please do spread out. Okay. So I sort of put this artery distribution here. Let's imagine you measure this one, that particular spin, and it's pointing up. And now what if I cover it up and I don't know its state? Then what state could it be in? It could be in a combination of up or down, which I write as A times up and B times down, with some coefficients A and B. What about the neighbor? Same story, C and D. A simple state that you could construct is simply the product of these two, and it would look like this, okay, with those coefficients. In the previous slide, I told you can make a superposition of up and down. You can make another superposition, right? That's up, up plus down, down, and there's no way to pick numbers A, B, C, and D that give you that state. That's interesting, right? If you try to actually kill the off terms, you can't do it. If you kill one of the terms, you lose this state, and if you kill the down state. So this is an example of a state which is not a product state, but an entangled state. Okay? And these families of states tell you really the complexity that it can exist in a physical system. Okay? And this is where you get this oft-quoted number. Okay? 2 to the power n, which tells you the number of combinations of these bits, is much, much greater than 2 times n. And if you take 2 to the power 300 and you entangle them fully, that number is so large you wouldn't be able to describe it even if you had all the particles in the universe, no universe available to you. So that's where that number comes from. It's 2 to the power 300. So the challenge of quantum computing is to build such a state and manipulate it. And that's where we're going to go. Does this phenomenon of entanglement actually occur? Yes, it does. It actually got the Nobel Prize, and bless his soul, rest his soul, that's Stuart Friedman, right, in the 70s there. And of course, we have also on Clauser, avid sailor. Don't know if Richard is in the audience. He can give us an update on Clauser. But in fact, this set of experiments in the 70s really told us that these quantum correlations do exist. We didn't use them for any particular engineering task, but it proved that they exist. You fast forward and you see all sorts of different quantum technologies now around us. Everyone has a qubit. You can build it in semiconductors, with photons, with trapped ions, with things that only we can imagine that are topological, or superconducting circuits, so on and so forth. To the point that beautiful experiments done in companies are showing us that we are able to put together quantum states that evade classical simulation. We haven't gotten to the point where you can execute a problem of import in computing, but we can cook up problems that are specifically suited to quantum, but we can show that they can't be done on a classical machine. So we're testing this idea of quantum complexity of quantum computing. Nothing's wrong yet. Nothing's wrong. Okay. How close are we, and what's needed to actually build a machine? You need really 3 pieces of the puzzle, and I'll touch upon these during the talk. Number 1, we need to build quantum systems where you can actually manipulate the quantum state. Not just observe it, but change it to make a particular superposition or an entangled state. That's the quantum control. And we need to do that. We need to change and measure quantum states faster than losing the information to the environment. That's the name of it. We have to be the environment that takes out information, but much faster than the uncontrolled. Number 2, it's not good enough to build 1 qubit. You need a lot. And the question is, as you start to put more qubits in, what happens to this coherence and environment? It gets more complicated. And finally, we need to think about, for a given set of hardware, what's the best algorithm to execute? In this particular field, historically, the theory came before the hardware. So we had the end of story use cases, Shor's algorithm, or factoring numbers, or breaking cryptography codes. The hardware is sort of still trying to catch up along that way. So there's a lot of things we can think about doing with imperfect hardware. That's really a subject of modern discussion and discussion. And this is not appropriate for a physicist. There's no axes, there's no numbers, right? So how far are we from this? Let me plot something for you. Okay. On this axis is how good you do whatever it is you want to do. So if you want to flip a bit, do you do that with 10 to the minus 7 accuracy or no accuracy? That's this axis here. And how many bits do you have? You have 1, 100, 100,000, so on and so forth. I love this graph for physicists because it can never be wrong, at least for a decade or 2. It's in log scale. All I do is I move by 1 millimeter every few years, the curve. Okay. So what's interesting here is if you look at this boundary, this is in some sense the classical simulation limit. This is what classical computers can do. This is currently art, and in particular superconducting qubits. The other ones are not so different, certainly on this scale. And the general features of this are that if you have qubits, you can make them very good. You can make the rotations, the gates, the logic operation very good. As you add more, we start to lose this fidelity. But we are getting close, right, to this intersection. It also tells us of how to interpret things in the news. If you make lots of bad qubits, it's not very good. You're not going to cross the boundary. Or if you make very few really good qubits, you're also not going to cross this boundary. So perhaps the most interesting thing is, how can I push this just a little bit more to solve problems of import? So what you'll see in this is really the quantum mechanics of open systems. And it's different than the quantum mechanics of atoms and photons. Not that the rules are different. What are next generation qubits perhaps going to look like? And moreover, are there things we can do to make the given hardware we have better or more powerful, in the spirit of extending this boundary along the diagonal? Okay. So I want to take a foray into superconducting qubits just to share the very basic concepts. The story starts actually in my mind with Nobel laureate Tony Leggett. You see, in the 80s and late 70s, it wasn't obvious that if you made a circuit of quantum mechanics, why should it be? This theory of quantum mechanics is photons and atoms. It seems crazy to think about a capacitor being quantum mechanical. But Tony certainly asked that question. Can you have coherence in a macroscopic system? Okay. And he particularly started to think about this object, which is a Josephson junction. Okay. And squids in a loop, and so on, and the like. But basically, a Josephson junction are two pieces of superconductor separated by something which is not a superconductor. In this case, an insulating barrier. So for such a structure, you have pairs and they can tunnel across. And if you think of these Cooper pairs forming a condensate, just like cold atoms form a condensate, they have a phase, and there's a phase difference delta across this condensate. Okay? And the idea would be, if this was truly quantum mechanical, for students here, you can figure out the current, right, that goes across this structure. It should be, of course, related to the gradient of that phase. Okay? And that's really the question, is it quantum mechanical or not? And if you believe it to be quantum mechanical, then this delta is basically like a position. It's a coordinate in an oscillator. Okay. Oh, that's a bit strange. It should be a much better looking oscillator. Ooh. Projector issues. Okay. I'm going to take one quick pause, see if we can do something slightly better. Those are nice pictures. It'd be nice to see them. It's the display. It's the display. Okay. So what's happening here? We have a board. Excellent. One must prove that we can actually lecture, right? We have an oscillator. This coordinate is delta. And you have your particle here, right? And this is the energy. And if it was quantum, at some point, it will tunnel through the top. Okay? And in fact, that was really the beautiful experiment that this gentleman and his team did, our beloved host. Okay? And this very famous paper of Debre, Martinez, and Clark that went ahead and actually showed the following effects. Okay, so again, let me that. You can calculate this rate gamma going through, and at some point you will be familiarly active, and then at some point you feel quantum fluctuations. And that's really the result that was called microscopic quantum tunneling. And you can kind of see that here as you go down. Right? But in fact, there were two other things that were also shown. Number one, if you have quantum mechanics, you have quantum fluctuations. And that should give you this rate, also shown by this team. And the third thing that this team showed, okay, those are the three pieces there, were that the levels here were quantized because you can do spectroscopy. So you see, this was really the shot heard around the world, because now you have this object, which was debated to be quantum mechanical or not, but it showed all the hallmarks quantum system. And this was really the first qubit, if you like, the phase qubit that came out of Santa Barbara and Google and what have you. It was, of course, John Martinez's thesis work that was done here. Okay, fast forward to 99. Okay. This is the first superconducting qubit per se that came out from many laboratories. And you see Joshan Sai, okay, and Yasunobu Nakamura. And Joshan Sai, just to point out, got his BA from the department here in 1975. Okay, so that was the first qubit. You can see it was a complicated device. And really what it was, the type of transistor, right? Just like a classical bit is a transistor, but this one dealt with individual charges, right? One Cooper pair at a time. So they made a transistor of Cooper pairs, single Cooper pairs. And they removed all the wires, because if you put wires on it, you kill quantum mechanics. So they put capacitors. So that was the recipe. Capacitors plus a transistor. And the lifetime they got was 1 nanosecond. Okay. And what I'll show you now is that we've improved by 6 orders of magnitude this lifetime from 99. So there's a lot of quantum mechanics happening under the name of quantum computing. Okay. So how do you do that? So this is now the one slide introduction to a modern qubit. This, and I apologize to all classical computing aficionados, is my reduction of a classical bit. All the billions of dollars in your Intel foundry are basically this switch, which shows you that you can go from 0 voltage to a finite voltage. Okay? And you measure out the bit by simply reading the voltage on a resistor. And the fundamental problem of turning this into a quantum system is that resistance takes away your coherence. If you've ever had difficulty writing the Hamiltonian for a resistor, it's for a very good reason. Okay. Because the resistance takes away all this information. So maybe there's a fundamentally different way to think about a bit. In fact, Planck had done this many decades before when he thought about explaining body problem. He said, if you think about physical systems, they have springs that are oscillators. And these oscillators take energy in and out in quantized units, like this. Why don't we use those and counting the number of excitations as your bit? That's a fundamentally different idea than using a transistor. It's using an oscillator as your bit. And if you use an oscillator, you can remove the friction between those elements. And that's really the key to get a long lifetime. And this is not so far away from what we do. This is a modern Transbond qubit. It literally is an LC oscillator. We've taken a Josephson junction, shunted it, right, so that the frequency is between 1 and 10 gigahertz. And here's an image that we put together in, I don't know, 2008 or so, of that junction of submicron dimensions. And the lifetimes now are order 100 microseconds to a millisecond with this recipe. It goes by the name which many of you have probably seen in the literature. That's what's called the Transbond qubit, just an oscillator. Okay. How do you read it out? You got to put wires on it. And the wires are the Achilles heel of all quantum technologies, because they are your link to the outside world. They are your link to a many-body system that can cause decoherence. This relies on thinking of this as basically an atom. And if you have an atom, a good way to read it out is to put it in a fabric cavity. Okay? So this is effectively an atom. You can adjust this cavity by the size of features. The antenna on it is adjustable. And if you do that, then the physics is described by the Jane-Scudder formula, which is here. So you have a term for the spin, which is sigma z. You have a term for the oscillator, like dagger A plus a half. And this is a simple exchange term, telling you how you swap excitations from the atom to the oscillator. If you detune these two frequencies, resonator and qubit, you can write it in the dispersive limit, where all you're doing is you're pulling the frequency of the cavity depending on the state of the qubit. So if you were to pass a microwave signal through that, that's the response. It would look different if you are in 0 or if you are in 1. That's really the principle of reading out these qubits. What's interesting is that separation depends on the number of photons in the cavity. Okay? And the width here depends on how long you measure. Okay? So you have a trade-off here. If you want to separate those histograms more, you pump more photons in the cavity. And if you want to make them narrower, you can integrate for different periods of time. And what I'll show you is in the simple limit, You just want separate to tell the difference between 0 and 1. But life gets much more interesting if you don't separate them. Right? Then you have a new flavor of quantum mechanics to look at. So we'll talk about that in the next few slides. The entanglement, though, is to separate those two histograms. You have to measure a microwave signal coming through this cavity. How intense is that signal? It's of order 1 photon. Right? And that's still to this day, commercially, you really cannot buy any amplifier that will do that. So that was when our host pointed out, that was the first problem, how to measure such quantum systems at the level of 1 photon, okay, or even less. And so I am reminded of this image, which I've kept for a decade, because it basically tells you how to amplify signals. Okay. You have your 1 photon carried by this innocuous bluebird. Okay. The innocuous bluebird is unable to convey to you the number of straws in its beak. So it must, of course, find a system which is sensitive to that. And here we have a camel who volunteered for that. The camel must, of course, already carry many pieces of straw so that it's in this regime where its legs are about to give way. Okay. So if you, of course, add the proverbial straw to break the camel's back, you will see, of course, a very large response. That's what you want in an amplifier, right? You want your 1 photon to cause a very big response. So everybody understood this and understand this in the technical domain. The problem is the falling camel walks on rocks. This is very problematic. Right? Camel is walking on rocks, its legs are wiggling for no good reason. Okay. What if the camel decides not to sit? It loses some of its, when you put that 1 extra piece of straw, the other pieces fall off. That happens in all classical devices, right? And it took us a while, community, to figure out is what you want is actually this relation. Okay. This is the relation that tells you how to make a quantum limited measurement. Okay. And the pieces here, let me walk you through that. There is a rate gamma m and a rate which is gamma phi. This rate gamma m tells me how much information I'm getting out of the system. This rate gamma phi is telling me how much dephasing I'm putting into the system, how much I'm scrambling it, because after all, it's quantum. You have to project that spin. Okay. So the question is, what is the upper bound on this? It's 1. Right? The best you do is extract as much information as you perturbed. Do no harm. This is basically not the hypnotic code for physicists, right? When you're doing quantum measurement, do no harm. Take as much out. So what actually goes into that? There is a gain called lambda, right? That's the gain of your amplifier. The more gain you have, the more information you pull out. Sensible. The more gain you have, the more back action or dephasing you have as well. But now we have 2 other terms, lambda prime and this correlator. Lambda prime tells you the gain in reverse. So this is interesting. Why would you ever have gain in reverse? Because you've got a resistor. In quantum mechanics, it's unitary. So in fact, you can take a noise that the camel walks on, and it gets amplified in the reverse direction. It's a non-trivial thing to get rid of. And then you have something that, John, you have loved for many years, this cross-correlator term. And what that tells you is that your weights at the input and output, the more similar they are, you don't have extraneous degrees of freedom that are taking away information. So that correlator goes away. So you see, if you want this to be 1, you need to get rid of lambda prime in this term, and then you'll have 1 in the ratio. That took this community a long time to figure out. And at the same time, we were developing generations of devices to execute this mission. Okay. Once we did that, you could measure individual events in superconducting qubits. Before this, we could never measure a single transition. We would always measure Bob and ensemble average decay, which always left us in the dark. Is it quantum? Is it not quantum? Is it really an atom or is it not an atom? No, it's exactly an atom. So here, for example, we would measure these individual jumps with this amplifier, right? Put a line in between and decide what spin up and spin down. And in fact, we could even take a histogram of those and reproduce for you the ensemble average. So this is going backwards, right? Rather than only having an ensemble, we formed the ensemble 1 shot at a time and showed you it was the same. But then we started to think about this question in quantum mechanics. Is that measurement instantaneous? How fast is the jump? Right? How fast is this thing? And if we take those histograms for measurement and make them overlap, we can slow down the measurement. And in fact, we can reconstruct the trajectory as it does this jump statistically. So we now had the capability to look at, if you like, the collapse of the wave function in some statistical sense. And here's what it does, for example, on the same. So you see, the founders of quantum mechanics were brilliant. They said the measurement results in the eigenstate of the measurement apparatus. Of course, they never told you how fast, right? Or how that happens. So we now had a window into these individual trajectories. So you see, in the search of this technology to read out qubits, we found a lot more about quantum mechanics. Then we started to think about things. Could you measure things that in not even thought measurable in quantum mechanics? This fellow, of course, wrote down a very beautiful equation, going back to this Heisenberg microscope. If you go ahead and try to read out the position and momentum of a particle going through a lens, you obey this hypothesis. That was the Heisenberg proposition. It turns out this relation you learn is not unique. In fact, you learn this one. This was written by Robertson, right? And in fact, Schrodinger himself wrote a more complicated one. So the more complicated quantum states you have, there's actually different families of uncertainty relations. But you notice the structure of all three, they're products of these uncertainties. And it turns out it's very easy to be on the trivial side of this. If you have, for example, n operator that's not in continuous space on a lattice, you can easily make this zero. So it doesn't tell you anything, it goes zero. So this is interesting. In 2014, Makona and Patti wrote an uncertainty relation that was the sum of uncertainty, which is never trivial. So we thought maybe we could go measure that, right, with this weakness. And what it would involve is measuring X and P simultaneously. And now you just sort of have to stop and think, what does that mean, right? What did Heisenberg tell you? Heisenberg told you that if you measured X, then P, right, and made a histogram of that, you would observe this. There is no time in his relation. There is no time parameter there. It is simply a statement of distributions. So we thought of the experiment. What if you measure for a very short period of time the position, then the momentum, then the position, then the momentum? What would you get? Right. And in our case, it was a spin system. So we measure sigma x and y in that case. So I'm going to show you a movie. And oops, wow. There we go. So I'm going to show you a movie where we go ahead and look at these individual trajectories, where I do this alternating measurement of X and Y. And as a control experiment, I measure X with X. Okay, let's see what you get. There. So these are two trajectories. These are two trajectories. Notice what's happening. They're going to eigenstates, right? Because at the end of the day, I collapse the wave function. What's happening here? They never collapse. So in fact, you can stop the function from collapsing altogether. That's pretty interesting. You can take out, the story of my life has been finding classical mechanics and quantum mechanics. So it turns out this quantum weirdness goes away, right? In fact, if you measure two quantities. And to your taste, Edgar, what's interesting is the mathematics that describes that is the Fokker-Planck equation. Completely classical on that. So again, very interesting how quantum weirdness can be suppressed depending on what you measure. Why is that technically useful? If ever you want to make a feedback circuit, you want to stop the collapse of the wave function. Right? A classical feedback circuit measures something and fixes something. You can do that, which we couldn't do before. And we did, in fact, to measure phase for the first time with quantum accuracy. Okay. Now, in the last piece of the talk, we need to actually do a computation with this. You put these qubits together and make a computer. Okay. So this is a zoom in of a chip. There's a bunch of qubits in a ring, typically 8 here. And we sort of start this slide with the premise of superconductivity. This is the greatest effect known to humanity. Right? All excitations are paired, no dissipation, all surfaces are perfect, right? We have no defects. Unfortunately, none of those statements are true. Okay. And in fact, Landauer understood that many, many years ago. So I'm going to give you the second quote in Landauer, which I thought was amazing. This proposal, like all proposals for computation, relies on speculative technology. It does not in its current form take into account all possible sources of unreliability and manufacturing error, and probably will not work. I hit it spot on like 2 decades ago. So in fact, there are defects on the surface. And with colleagues, VNL, we really got a window onto what's happening on all these surfaces. Okay. So this really, for the first time, we had a sense of, at the atomic scale, what was the structure or lack of structure in the amorphous oxides that are there. In particular, we were looking at iodides on the surface. How much Nb2O5 do we have versus other particular stoichiometric species? And we learned a lot. And from this information of how to remove these oxides, we improved the quality factor by a factor of 10 to 10 millionths of photon cube, which I don't believe is matched to my knowledge in this day. So actually trying to understand, at the single photon level, what's happening is amazing. And John, we got something also very interesting us. It turns out, for those that are aficionados of flux noise, Nb2O5 is less mismatch from niobium. And in fact, under strain, it develops a magnetic moment. And in fact, it gives you the right areal density for flux noise. Well, an interesting, perhaps, direction to look at a 40-year-old flux noise. Okay. What about the junction itself? Zooming in on those properties, here's a cross-section that's here. And in fact, this is a 10 nanometer scale bar showing you the composition of aluminum and oxygen as you go across. We now have the ability with colleagues at LBNL really driving this, look at what is in fact the ratio of aluminum and oxygen in a junction. And it varies on some very, very small scales. And how does that introduce noise? This is a contemporary topic of research. Finally, before I show you results of some simulations and then go to questions, you see this discussion of which qubit to make. I showed you something that was, I think, incomplete at the beginning. I showed you semiconducting qubit, superconducting qubit on. One must have a discussion of the and the environment together. So every proposal for a qubit should tell me what I need to do in the environment. Okay. So now let me put that degree of freedom into this discussion. Here's the Transbond qubit. You can see the circuit is very simple. There are 2 observers. This is the noise full of environment full of noise, excuse me, that's there. Whether it's surface defects or quasi-particles or whatever. There is the graduate student observer, Beaker. And you see, in this game, the fabrication is very simple, but Beaker has the same kind of lines as the environment, so Beaker just has to be faster than the environment. So you just need to be faster than your environment to get some information. But that's a hard proposal to win, especially if you add more qubits. What if you make a different type of qubit? By adding more junctions, you can reduce or gray out some of these couplings. A Beaker has a better shot. And you can keep on increasing the complexity of your junction and playing this game till you get to a point where you have a circuit which is difficult to make, but in fact, very weakly coupled to the environment, may also be weakly coupled to Beaker. And that's really the difficulty of moving along this trajectory. But there is one powerful concept here that I want to convey to you. You see, this first encoding is an encoding in Cooper pairs, because we're using a superconductor. These more powerful encodings are encoding in pairs of pairs. You see, this is 4E transport, or pairs of plugs. And that's a powerful concept, right? If you can go ahead now and do this, then you can decouple yourself from many, many sources of noise because they don't have the right parity to couple there. And that's active sub-research in our lab and in other places. What's the challenge in these devices? Building some of these components is very difficult. We'd like to build inductors that have very little capacitance. Here's an array of junctions where we've removed, Christian Junger here has removed the substrate underneath. This is quite wild. You see this they're all Josephson junctions just hanging out. Right? And if you do that, then you can enter a very different regime to the point that we can see nice nonlinearities, nice resonances, and we can also start to see new physics. If you look on the minute time scale, you have jumps, maybe they're facelifts. Maybe you can measure individual ones or other excitations. So again, this dichotomy of technology and physics. Every time we uncover a new technique, we find some new ideas. Can you build a qubit out of it? Yeah, you can even curl them up, although you didn't really do it by choice. But nonetheless, you can curl them up, put some small junctions there. Yeah, and he makes a qubit. Starts to see those lines. So again, we're kind of pushing this direction of let's try to make more complicated devices. And I do want to also make a note to folks that work in the field of quantum materials. To me, this choice of qubit and qubit lattice is the ultimate quantum material in some sense. Because you see, natural quantum materials are where the experimentalist encourages, I hope you agree with this, Bob, encourages the system to form a certain structure, whether it be a sheet of graphene or what have you. You were just pulling the string so that you get some very pristine material. Okay. And in fact, symmetry and structural perfection, these are good things, because in fact, we're going to look at the collective response of this. However, now I need to measure it site by site. So when you build a qubit, in fact, it's a complete design and synthesis of quantum matter. What lattice should I use? Should it be a perovskite? I don't know, right? How do I go ahead and lay out all of these qubits for optimal operation? So in some sense, it's the ultimate quantum material that you have. And moreover, you're going to break the symmetry no matter what, because you need the information in and out. So it's a different type of synthesis problem. Okay. So the final piece, can you actually do something with even the hardware at hand? Okay. You want to execute something like this. This is a quantum circuit where each one of these lines represent a qubit, and each one of these little boxes represent a gate, a rotation of sorts. And the problem, of course, is that the lifetime here is finite, so I can't stack too many rotations. Right? I'm going to lose phase coherence as I go across. So this means that the depth of the circuit is limited. To give you a scale of what we can do, if you had 500 microseconds and your basic gate was of order 1 microsecond, and you have a sense that you can do 500 flips, it's a bit less than that because you want to make a logical gate, like a C0, Control Z, or what have you. But one gate is not enough. You need several of them. And that gives you a sense that we're talking about tens of gates. Okay. What's the problem? Is decoherence the only problem? Well, we put in all these wires, right, to keep all that decoherence channels out. It turns out it's worth looking at a matrix that tells you the different type of errors you have. You can have errors that are stochastic. These are ones that cause dephasing or loss to the environment. Or you can have errors that are just a misrotation. So this one preserves the purity of the state. It's still on the Bloch sphere. This one causes the state to shrink because it's only statistical. And what's interesting is the matrix for these types of errors is diagonal. The matrix for a rotation looks like this, which we've all seen in quantum. And these off-diagonal elements are actually particularly pernicious. The ones on the diagonal are cosine, scale is theta squared. The ones off the diagonal, scale is theta. So the error is worse. And moreover, if you want to concatenate the error, imagine you multiply all those matrices together, one after the other. So the diagonal ones scale in a very easy way. The off-diagonal ones start to get pretty messy as you multiply. So the question is, are we really dominated by this kind of stochastic noise, or are we dominated by the coherent type? I'm curious, what do you think? How many of you think that we would be dominated by things that cause T1 and T2? I will do a final question, which is, what if you have no vote? So, but what if how many of you think we're dominated by over rotations? Okay, so you would be right. That's not the problem. It's actually crosstalk and other things that's killing us. And we just measure. That's the actual matrix that I showed you. We can actually go ahead and measure that for a particular 2-qubit gate. And you see, yeah, there's a lot of weight on the diagonal. There's a lot of diagonal. And the question comes in, can you convert this noise, which is off the diagonal, to the diagonal? So what that our group in particular Dr. Akil Hashim has really pioneered here, is to think about how to add randomizing rotations at each step, because that's coherent error. And in fact, you can see even with 100 randomizations, the error model is now almost diagonal. Okay. So that's completely changing the noise environment. And moreover, it allows us to do much more complex simulations now that we couldn't have done before. And I'll only give you one example of this in certain patients to make better algorithms and also more reliable. Paying homage to the nuclear physics community, if you would like to have a simulation of scattering events between nuclei, say, then you can write some lowest order chiral effective field theory, as shown in Feynman diagrams here, where you go ahead and break up this effective field theory into a spin-independent and two Hamiltonians. And then you want to actually propagate the state forward with a unitary operator, U of t, which you discretize. And you can break up this unitary into, in fact, two pieces, the spin-independent piece, 221b. You remember this? This is what we did. That's the trotterization into two pieces. So people actually, okay. So you can go ahead and encode these four scattering states onto four states of your qubit, and then go ahead and try to write a unitary, which is here, that shows you the evolution of the system. So that's really the quantum piece. Half of that Hamiltonian you advance using your quantum scatter. You can look at this. These are C0 gates. This cell starts to get heavy, right, given the number of gates that I have. And if you run it as is, what's shown here, the dots are in fact the exact, the dots are the quantum result, the lines are the precise calculation. There's a tremendous error in between what you get with the quantum system and what you get in the calculation. However, we can start to put in this randomization, things get better. We can also now go ahead and try to adjust the length of that block vector, right? Because it shrinks because of the stochastic noise. And at the end of the day, you see we're doing a hell of a lot better in running a simulation like that. So improving and even tailoring the noise that you have in your system, having some knowledge of that, is powerful. So what's needed to go from to some real computer? Well, I want to sort of present you this problem before I give you this up. You see, the development of classical technologies, which in fact was spearheaded here a lot at Berkeley with noise and so on and so forth, had really the development of an integrated circuit. You can go ahead and plug different devices in and make it work. We don't have that in the quantum domain. For a single qubit, it's bespoke. You'll spend $100 million to make one qubit. Now you want to go change it. That's an expensive proposition. So in fact, what we are, I think, limited by is, and we are living in an era not of quantum advantage, but classical disadvantage, right? Because the classical pieces are too heavy to allow you to actually go ahead and explore that space. So in fact, the lack of quantum-tailored, resource-efficient solutions to control quantum processors severely limits our ability, at least in my field, to study different qubits and architectures. And if we unlock that, then we can go ahead and look at all those possibilities seamlessly. So at least from my point of view, this is a tremendous enabler we should think about. So to conclude, one side of this coin is quantum computing, the other side, quantum foundations. In the 80s, we spent time thinking about superconducting Josephson junctions and whether or not they obey quantum mechanics. The answer is they do. Then in the 90s, we realized that we need to remove the environment to see this quantum mechanics. You can see it. And we got controlling them. And then we spent a lot of time on measurement and trajectories, which I showed you. And I think in the 20s, we're thinking about many-body entanglement. That's really the ultimate test of quantum mechanics. Does it work when you have that many entangled degrees of freedom? I don't know. We change our theories of physics every 150 years or 100 years. Maybe it's not a bad idea to think about this one. So nonetheless, the journey has culminated, at least in my co-conspirator, Professor Andrew Jordan, and myself, in writing a book on these new ideas in quantum measurement, which hopefully will be out this year from Cambridge University Press. So with that, I take your leave and the floor is open for questions.
Question or so?
Yeah, so with regard to adding noise and how that improves your measurement, if I understood that fine, is that similar to nuclear magnetic resonance measurement? In a liquid, you tend to get sharper lines because the atoms of their nuclei are experiencing a variety of
Right, so there's functional narrowing in that particular effect. Not there. I think they're similar in spirit. Here is simply changing, coherent noise, which scales as linearly in a particular object, incoherent noise, which scales the square root. That's basically what's happening. The other physical way to think about this is that when you do a rotation, you could be very unlucky if they all add up in the same direction, right? And that's the worst possible case. And that's the case you need to consider for a fault-tolerant machine. If you just have random noise, it's a much more stable scaling, right? Because it's a randomization in the environment. So motional narrowing, of course, has that field.
Yeah, about the random noise. What kind of noise? Like uniform or rocking?
Yeah, that's a great question. So in fact, it's noise in the sense of what your tool set is. Your tool set are rotations. So there are random rotations on the Clifford set, say. So we're putting in random rotations. And of course, if you come up with different iterations of that circuit, each one of which have random rotations, and then average all those circuits, then that stochastic piece averages out.
So I've had just basic questions on quantum computing. A classical computation, you put the input in and you get a very good answer. The advantage of my understanding of quantum computation is that in the quantum computer, because of entanglement, that's presenting all the different possibilities that are seen. So my question is, when I make a measurement, how do I get the right answer? I have 10 to the 300 different possibilities in my quantum computer before I measure.
Right.
How can I get the one I want?
So the idea, Chris, is to come up with an algorithm that takes advantage of that many base, but gives you determinate answers, right? A classical example of that, young Andrew here, who just finished from 137A. I ask him a question, and I look the other way, and you poll everybody in this class, and I ask you for the answer. So the question is very well posed. The answer is very well. The computational space he has access to is much.
It bothers me that you base your ideas on ideas that cannot be tested. In other words, you can't test them with things that the right? And then you're stuck with trying to experimentally determine which one is correct. It should be that you base your ideas on things you can be tested. You can tell if you're on the right track or you're not on the right track. You don't have to worry about from your experimentalists what we looking for.
Yeah, that's a great question. So let me answer it in two ways. So first is a philosophical piece. You see, I'm an experimentalist. I believe in nothing. Right? I put stock in nothing. Right? Because the point is, I believe that there is a reality which is complicated, and I only have a small window into it. So anything I write is a per person's approximation to that. So I'm not putting stock on this as being the final piece of life. But the second piece of the answer is, yeah, it's fully testable. I write an algorithm and it does it better than my classical computer. So at the end of the day, that's the proof. Right? Can you do something in quantum mechanics that you couldn't with classical mechanics? It looks like yes so far.
Yeah, that's the key to the coherent driving factor. Already using that. Is that the end, or is it a wall, or?
The answer can depend on whether I'm a corporation or a DOE scientist or a DOD scientist or someone looking for funding from the Moore Foundation. So let me answer that in the most politically correct way that I can. I don't think we hit a wall by any means, but the real question is, how good do I get to call it done? Right, and that's the harder piece. So if you were to take the quality of qubit that we have and the architecture of error correction code that you have, you would require 100,000 physical qubits for each logical. That's a tough proposition. If I get better, I would need less. If I use a better error correcting code, I may need even less. So I don't think we've hit a wall, but it's this kind of coding saying that I need a better scheme to put these together, and then sort of improve the materials to go hit that.
To make it more complicated, you expect that there's a certain point of complication where you have to mention returns or maybe worse. Is there a maximum complication?
Yeah, that's a great question, Ed. So the question is, how complicated can I make it and still have utility? I don't know. That's what we're looking for. Because I think what we've had is you make it really simple where your environment is perfect, or you make the qubit impossible to make in the environment have almost all possible imperfection. To me, it's actually the same. You just change the label of environment and in both things, you still need to come up with something that was impossibly difficult. The thing was, in the first case, you never thought about the environment. You just looked at the qubit and said, oh, the qubit's really simple, but the environment is impossibly difficult.
Thank you for the talk. How does like a topological process and what do you mean? What would you add topological process?
That's a great question. So the general premise of this topological quantum computing is to take a Hilbert space that fractures into two pieces where no local operators connect. Okay, so you go ahead and have no noise operators on one state, being completely decoupled from the other. The challenge, of course, is to write the unitary that works on all, right? And to turn that on and off where the first assumption is not broken, right? So this thing is very difficult to do. If you were to think of a Majorana excitation or a self-excitation, yes, you can come up with things of that nature. But at least as an experimentalist, I don't know how to do superconducting qubits. It's a hard problem. So I'm just saying that there's a whole zoo of things that you can do, noise bias to noise protected to noise suppressed, before you need to get to that full topological piece, which is kind of what Ed was asking for. How far do I need to go down? Not known.
So on the slide when you're showing how state vector velocity are evolved, and if you cycle the measurement, then you essentially have control over the evolution of those. Versus if the class is an activator. So do you think that doing different types of cycles, like cycling with different operators, could help us understand exactly what are the working forces that that arrow around?
Yes.
And what's the difference before that class is
That's a great question. We did it. I didn't have time to show you the experiment. So the first thing that you can do is you can go ahead and take that partial measurement result and readjust your measurement apparatus. Because let's imagine you want to measure the phase of a vector. So here's a vector that's pointing somewhere. The phase means you should measure not along the length or orthogonal. The problem is you start the measurement, you kick the vector. To change your measurement axis before the system collapses. And we did that, and it was the first measurement of quantum phase. And it beats, if you like, heterodyne for classical systems. So yes, you can. So again, there's a piece of technology coming out of this very basic physics experiment.
So I have a somewhat broad question.
Yes, sir.
You and I work on superconducting things,
Mm.
and I spent well over a half century of my life doing that. Tons of proposals for quantum computing, quantum qubits, and so on, and everything from semiconductors to atoms and so on. Now, do you personally believe only superconductors will win out?
No. So let me also give an answer to that. I think all quantum technologies are great. This is not a political answer, it's a real answer. Why is that? Because they just solve different problems, right? For example, if you have an atomic array or a Rydberg simulator, it's looking at a different region of physics, right? And you learn something different. So all of these approaches are rather complementary at the moment. The nuance is if you want to build a machine, which is a true universal computer, which one of these will enter? Then I raise the question, well, what's going to build the memory of the computer and what's going to build the processor? Where's the cache? Where's the data, and so forth? So you kind of need a combination of open closed systems. So life is not so simple as to pick one particular modality to do it. So I think that's sort of my take on it, saying that if you want to build a quantum memory or do other things for error correction, you may need a different system.
You mentioned a bit that when you out, you need have an ecosystem to give you competition. And you said you don't have a what do you think needs to be done to make that?
Right. So I think, all fields go through evolutionary tracks. So we are getting to the point where we're realizing that it's not such an easy problem, right? So it's probably worth having a discussion and trying to lay out a roadmap. And that's one of the things we also are trying to do at the moment, is to lay out a roadmap for what are the critical challenges that need to be overcome. So I think that would be a big step forward. So there's software and there's algorithms, right? So there's a whole different field of an array of things that are there. For example, firmware, gateware, software, so on and so forth. So there are hardware challenges of how to actually efficiently go ahead and upload information and offload information from a quantum device. After all, you want to store the information content of the universe on the size of a postage stamp, right? So somehow information needs to get on and off that in some efficient way. So there's one level of complexity there. Then the algorithm piece is, even if you were able to control it, what's the right way that takes into account the physical structure, topology, and so on and so forth. So those two things are together. And what I was referring to in that slide was more the algorithm piece. That's there.
Maybe not quite.
Let me ask a different question about quantum mechanics. It seems to me that at least I've always felt that the collapse of the wave function sort of an
Yeah.
You apparently now can actually measure this. But is there a time scale and changes in performance?
Yes. Measure is a very delicate word in quantum mechanics. So let me answer the second piece first. Yes, there's a time scale. Measurements are fundamentally continuous, right? And one can go ahead and change that time scale depending on the that you have. No problem. Measure means with level of determinants, right? In quantum mechanics, it's interesting. When you know the spin is up, it is up. So if you know there's only 50% possibility that it's up, then it's within some band that's 50%. So what we've done here is we can statistically guess what's the most likely position of the particle. You cannot measure it because once you measure it, it's there. But how do you verify your trajectory? We can measure an ensemble, a family of them, right? And do tomography point by point and show you that our guess was in fact the most likely spot. Does that help with the picture? Okay. All right. So there are two pieces to that. There is the lattice mismatch between niobium and niobium oxide. This is fact. So one can go ahead and measure that. The rest of it is conjecture, right, of different flavors. So Shane Redding, one of our colleagues at the Molecular Foundry, has done a calculation of what happens to magnetism when you have this lattice mismatch. So that exists in a paper. You can generate some density of magnetics. Beyond that, we have no knowledge, only conjecture. It is something worth looking at and seeing if this set of spins, in fact, contributes to the flux noise. Be a great experiment.
There is more than one niobium oxide.
Yes, there is. It's NB205 that seems to be the culprit.
One last question.
So when you said at the very end that trying to build like this full quantum computer would be the ultimate test of quantum mechanics, are you worried that it's like quantum mechanics is like broken some way, or is it just that it would be unhelpful if trying to describe a system that just has too many moving parts?
Like I said, looking at the previous comment, I believe in nothing. Right? Everything is descriptive. Have we found the final theory of complexity, for humanity? Probably not. So there are places where quantum mechanics, of course, has difficulty reaching other theories of physics, right? Whether it be gravity or other places and so on and so forth. So I think the story probably is a bit more complicated, right? What about internal degrees of freedom? Do you have other dissipative bows that come on site? Do your correlations actually decay, right? With some exponential scale, that's what you would need for fault tolerance. You see, Andrew, this fault tolerance is a very fantastic concept. If you needed classical components for each quantum bit, it would never work, right? Because the complexity is increasing exponentially. At some point, you're able to suppress errors so that in a collective system, fault tolerance suppresses that error exponentially. I'm not sure that happens. I mean, we see it in the latest Google experiment, right? For 5 and 9 qubits. But to see that at some large scale, this is a task worthy of physicists and engineers to look at.
So let's thank Irfan once again for explaining.
Thank you.
Congratulations.
But I drew it for you.